put it that way, was doing odd-even splits. So I'm proving the Ramanujan identity using odd-even splits of Euler's formulae for the unrestricted partitions. Okay, so I like simple proofs, so I want to see where exactly things are coming from. Now what about the theorem with the parameter A? Is there some interesting trick involved? So we'll see how to prove that. Here is the series for the thing with the parameter A. I now look at the denominator and I expand the denominator using the Q binomial theorem. So these are the Q binomial coefficients, base Q squared. Okay? I expand. Now I put n plus j equal to m, and I rewrite it. N plus j is m, so I put a to the m, q squared, n plus j comes out, n minus 1 comes out, so that's that. Then I take the rest and I rewrite it in this form. So proving Ramanujan's identity is the same as proving that this is q to the m squared. I like to think of this like a sieve identity. Right? A lot of cancellation, only the squares are surviving. Now I divide by this product, so I want to prove this identity. Now let us use this same idea. See, the ideas are all still the same. What is m squared? It's 1 plus 3 up to 2m minus 1. I think of it as the minimal partition into distinct odd parts. So the generating function for all partitions into distinct odd parts by the same idea would be q to the m squared divided by 1 minus q squared, 1 minus q to the 4 up to 1 minus q to the 2m. But here I have only up to 2m minus 2, which means this is partitions into distinct odd parts where the smallest part is 1. Okay. So once I have that, I multiply by z to the power of m, and this would be the product. Smallest part has to be 1, and I have distinct odd parts. Now here is a little trick we have learned in school, right? Our teachers have always said, we do not like irrational factors in the denominator. For some reason. So we always want to rationalize the denominator, right? And then you're supposed to have found the answer. If the thing is 1 over 1 plus square root of 2, you can write it in terms of 1 minus square root of 2, then you're supposed to have solved the problem. Okay, so I go back to my school days, and I say, basically what you're doing is you're putting in the missing factor, the conjugate. So there are factors missing here. The factors that are missing here are the evens. So I multiply by the evens, and I divide by the evens. So now I end up with the full product from 2 to infinity. Alright, so when I get the full product from 2 to infinity, I end up with this divided by this. This is just partitions, ordinary partitions, but q is replaced by q squared. So I just written down the generating function for partitions with q replaced by q squared with the change of sign. What about this? This is exactly like your partitions into distinct parts, triangular numbers, but in the embedding, since I want the smallest part to be 1, I'm never going to fill in a column of length n. So that is why at the bottom, this is 1 less than the triangular number there. So that's that. Now I compare the coefficients on both sides, and I get precisely the convolution that previously gave me the q to the m squared on the right. And therefore this little trick proves Ramanujan's identity. Again, coming back to partitions into, the fundamental partition theory. But it involves the trick. Alright, but you can always ask, what are the implications of a trick? Okay, so my question is, I perform this trick on isolating the first term, zq, and then looking at the zq cubed. Isn't it more natural to look at the full product and perform the trick? So let's perform the trick on the full product. So that's the full product. Missing part, I get that. Compare coefficients, I get this identity. I'm doing the whole thing in reverse. I now multiply by z to the power of m and sum. I will get this. So I'm just doing the whole thing in reverse. And when I do the whole thing in reverse, I'm just stepping up the speed a little bit to meet Professor Zauberger's 548 deadline. So we've got that. I end up with a series which looks remarkably similar to the Ramanujan series, with two small changes. This is Ramanujan's series. There is an n here, there's an n minus 1 there. My series has an n there and an n plus 1 there. So I first wrote this down. I was actually flying to Asia, and I said, this must be some sort of jet lag. I made a mistake. I mean, how can these two be equal? All right, they are actually equal. Okay, it's possible to compute that they're equal, but this is a Q-theoretic proof that they are the same. I want a combinatorial proof that they are the same. So why is it that the two are equal? And I'm going to give you a combinatorial explanation. So one question you should have asked yourself is, what is so special of having partitions into distinct parts where the smallest part is